Welcome to this video lesson. In this video, we will be looking at the power loss within power lines. We're going to look at a power station, and in this power station, we can see that basically what we usually do is we burn something, and that burning will create some heat energy, which will turn water into steam, and that steam will start turning some sort of turbine. And as that turbine is turning, we are going to turn that mechanical energy into electrical energy. And basically, we've looked at induced current. So if you have a magnet that's moving back and forth, it will create it will induce a current within this coil. And that's exactly what's happening here. So there's going to be a certain amount of energy that's being created. This is going to be the chemical energy or used. A certain amount of energy used, and that energy is going to go into mechanical energy, and that mechanical energy is going to turn into electricity. We're not going to worry about any energy losses or any inefficiencies that are happening in here. We're going to say that the total power output from this power station is going to be 500 megawatts. And mega stands for 10 to the 6, is a prefix for 10 to the 6. So that would mean that is 500 million watts of power being produced by this power station. As the electricity is being generated here, we can measure the potential difference across here, and that's going to be the EMF, or the amount of energy that each coulomb of charge is going to gain as it's passing through this set of coil of wire. And then the electrons are going to carry that amount of energy, or certain 1 coulomb of charge is going to carry that amount of energy and try to get it from the power station all the way to your house. Using this idea that we have the power and the potential difference across this coil, we can also find the current here. We can find the current, and that current is not going to change across this wire until it reaches this point over here. So let's do this. Let's measure the, and let's calculate that. So we know that power 1 is going to be equal to the voltage rise, or the potential difference that's there. We can also change this to delta V1 if you wanted to, multiplied by the current. This will help us figure out the current, so that's P1 over the EMF. P is 500 million divided by the EMF, which is 20,000, and that would give us 25000 amps for our current. And again, because this is only one wire, we're not really splitting the current anywhere. That would mean that the current across all of this wire is going to be the same amount. Now, this is the power that's generated at the power station. But as the electrons are passing through this wire, they are going to experience some resistance. And that resistance is actually increasing as the wire's length is increasing. So basically, the resistance value that we have here is based on certain length of wire. In power lines, if we use longer wires, this resistance also increases. So we have to kind of balance how much length we have, so that we don't damage the wire. And there's so many different parameters that we really need to take into consideration. But let's say for a certain length of wire, which is a good length for a power line, or at least a portion of power line, our resistance is going to be approximately 0.1 ohm. So as the current is passing through this, it is going to start losing some energy or some potential. So we kind of want to calculate that amount. We want to figure out how much is the total power that's passed to the other side, and how much is the total amount of EMF that we have on this side. And if we were to place a resistor here, so imagine that all of this wire's resistance is added to this resistor, sorry, so the 0.1, so all of the resistance within a wire is kind of concentrated in here. I'm going to call that well, we already have it as R. The amount of potential difference that's lost here is going to equal to the current multiplied by R. The R value is just this R here. It's not going to change. And the current we've already calculated, that's I1. So I can figure out the total amount of voltage or the potential difference that's lost as our charge is moving from this portion of the wire to this portion. I can do that, and I'm just going to do it here. Delta V is going to equal to I1 multiplied by R. I1 is 25,000. R1 is 0.1. That would mean I have to move the decimal point by 1, and I am going to lose this much amount of potential when my electrons are moving from here all the way to here. Assuming that my charges as they were going here before moving through here, they had zero potential, they are going to have approximately 20,000 joules of energy here for 1 coulomb of charge. They're going to lose 2,500 going through this wire. So the remainder is going to be here. So I'm going to calculate that with red as well. So EMF2 in this case is going to equal to the EMF1 minus I1R1, or just delta V, and that's going to equal to 20,000 minus 2,500, giving me 17,500 volts. So that's the maximum potential difference that I can have in this region over here. Now let's talk about power loss as well. So power loss is the amount of power that we lose in that resistor, and power at that point is going to equal to I multiplied by the change in potential. The change in potential right here is given as I1 times R1, and the current going across that one is also I1. I'm going to replace delta V by I1 times R, and that would mean that I get I1 squared R as my equation for power loss, and I am actually going to highlight this because it is a very, very important equation. It tells us that power loss is proportional to the current squared, and it's also proportional to the resistance. So as resistance goes up, power loss increases, but as the current increases, the power loss increases much more. It's just much more, the current here is much more significant compared to the resistance here. So how do we measure this? Power loss is going to equal to I1 squared. I1 is 25,000 squared. We're going to multiply that by 0.1. And this will give us 625,000,000, which can also be written as 62 megawatts, or 62.5 megawatts. That's the power. So that's kind of like the power that we lose. This, I should write it as 62.5 megawatts. So I'm going to change that. But the final question is actually asking me to find power at this stage. So we had a total of 500 megawatts of power here. We are going to lose 62.5 of it here. So to find power 2, that's going to equal to power 1 minus the power that we lose, and that's going to equal to 500 minus 62.5, giving me a total of 437.5 megawatts of energy available at this stage over here. To write my final answers, I have to look at the number of significant figures of everything that's given to me. I have 3, 3, 3 in everything, so I'm going to turn all my values into 3 significant figures. Everything that's requested, so power 2 here is going to equal to approximately 438 megawatts, or you can write it as 4.38 times 10 to the 8, or you can just write it as a value, 438 million watts as well. And for EMF at stage 2, that's going to be approximately 175 or 17,500 volts. And those are correct to 3 significant figures. In addition to all of this, we can also figure out what was the percentage loss of power that we had. And we can basically do that by dividing the power loss by the total amount of power that we had initially. So I'll write that in pink. Percentage loss for power is power loss divided by power 1. That's going to be 62.5 divided by 500. And these are all megawatts, so the 10 to the 6 is going to cancel out. And if I put that on my calculator, I will get 12.5% losses just by our electricity going through a wire, and not even a big distance. We are going to lose approximately 12.5% of all the power that was outputted from our power generation. So that's not even all the power that was used, because we used even more fuel to get that much amount of power. There was problems with efficiencies here, and there's even more problems with efficiencies here. So how can we reduce this? That's going to be our next example. Alright, in the second example, we have a similar situation. We have a power plant in which fuel is burning. That energy is thermal energy that's being converted to mechanical energy of the turbine. The mechanical energy is being converted to electricity by a generator that's located here. And basically that mechanical energy is inducing an EMF in the coil over here. We have 500 megawatts of power, 20 kilovolts of EMF in the first coil, and then this is connected in a transformer. And transformers usually have very good efficiency, so we're going to assume 100% efficiency on the transformer. So all of the 500 megawatt is also transferred here. But since there's more coils here, the EMF has increased, and we have 500 kilovolts in this region. Now, the difference that this makes is that we're going to have a different amount of current passing through this section of the wire. And I've connected these wires. I'm actually going to disconnect them. They actually don't connect like this, because otherwise they would have the same current passing through them. But they're connected in some other ways, but that's okay. And we have a certain amount of current. Let's figure out exactly how much current is going through this. We have the power, we have the EMF at that point, so power 2 is going to equal to the EMF 2, or you can also call this the change in potential difference, or just the potential difference at stage 1 and potential difference at stage 2. But I'll just use EMF, so it's EMF multiplied by current 2. And I'm trying to isolate for I, and that's going to equal to power 2 divided by EMF 2. And power is 500 megawatts, so that's 1, 2, 3, 1, 2, 3 for 10 to the 6. And EMF 2 is 500 kilovolts. So 500 and kilo has a prefix of K, which is equivalent to 10 to the 3. It's going to equal to a current of 1000 amps. And let's see if this makes a difference in amount of power loss and in amount of the total amount of potential that we have on the other side. I'm going to create a resistor here. Imagine we have the same resistance as last time, so 0.100 ohm. And we can start calculating delta V here. Delta V, or the potential drop here, is going to equal to the current. This is I2 because the current across this wire will not change. So we have I2 multiplied by the resistor, or the resistance. And the potential drop, delta V, is going to equal to, forgetting my subscript here, we have I2R, that's going to equal to 1000 multiplied by the resistance, which is 0.1, and that's going to equal to 100 volts. So that's the amount that we're dropping now. So to calculate the total amount of potential we have on that side, basically we had 1 coulomb, what 1 coulomb of charge has gained about 500 kilojoules of energy here, but it's lost about 100 here. So to see how much it has at the end, we're just going to subtract 500,000 by 100. That's E2 minus the drop. So this is the amount that it gains. This is the amount that it loses. So the amount that it has at the end is going to be 499,900 volts, which is much bigger value compared to my last one. And I will write this in 3 significant figures. This is going to be to round this, round this, round this. So this is actually going to be 5.00 times 10 to the 5 volts, which is very similar to what we had before actually, with the error was so small that it actually didn't change anything within our uncertainty. Now let's check power loss. The power loss here is going to equal to I multiplied by delta V. And we have the equation for it already from before. We know that, but let's just redrive it again. We have delta V is equal to I2 multiplied by the resistance. And that's going to equal to I2 squared R. So the power loss is going to equal to I2 squared R, which is going to equal to 1000 squared multiplied by 0.1, giving me a total of 100,000 watts that has been lost as these electrons are passing through this wire. Now this is good. I'm just going to write this in 3 significant figures. So that's 1.00 times 10 to the 5 watts. And let's compare the amount of power loss in terms of percentage here compared to the last situation. So we have percentage loss for power is going to equal to power loss divided by the power 2 this time, because it's the power from this region, and power 1 and 2 in this case are the same anyways, and we have 100,000 divided by 500 million. 23123. And in this case, we will get approximately 0.0200%. Comparing this with 12.5%, this is even less than 1%. We get a much smaller amount of power loss when we change the potential difference, increasing it. And the reason for that is we are reducing the current here. When we reduce current, that means the amount of electrons that are going back and forth, in this case we have AC current, are going to reduce. And as the amount of electrons that are going back and forth reduces, or even if their speed is reducing, that would mean that there is less collisions of the electrons with the lattice structure of the conductor within the wire per unit time. And if there's less collisions, that would mean that in general, the speed of the atoms or particles within the conductor of the wire is going to be lower. That would mean that it has a lower thermal energy or temperature, and that would mean the power losses due to thermal energy is going to be much lower. The main equation that we have over here for power losses or for power loss is I squared R, and that's the one you need to really remember. And again, power loss is proportional to the current squared, and it is also proportional to the resistance if the current is constant. If the resistance increases by a little bit, power loss is going to be proportional to that, so it's going to increase at the same rate. But if current changes, this is going to change by a factor squared. So if current increases by 2, this is going to increase by 4. If this changes by 3, this is going to change by 9, or 3 squared. So keep that in mind. You want to keep lower current in order to reduce your power loss in any situation. I hope that this video was helpful, and I hope that you have a wonderful, wonderful day.